Right.
Could you please switch off your microphones? Could you kindly switch off your microphones? Thank you. All right, so just to find out if people have any specific questions with regards to what we covered the last time we met. So we started our discussion on lecture series number 14, which is number systems and representation. And we actually started off by we're going to continue with these different usage scenarios, just trying to set the stage for application of these things we're calling number systems, right? It turns out that information when it comes to computing is sometimes conveyed using certain number bases. So we discovered that, in fact, what we had discussed as part of lecture series number 13, this whole notion of how permissions represented numerically on Unix-like operating systems actually makes use of base 8, which is why the maximum possible number that you can have associated with either one of those three groupings is a 7. The minimum is obviously a 0, right? And we've seen this over and over again. So if you look at this particular screen grab here, you realize that the permission here is 600, right? 600, yeah? We discovered that the maximum possible permission that you could have is a 777, right? Which means everybody has read, write, and execute access, right? So just setting the stage here. And then we also highlighted the fact that some of these errors that we get to come across when we are using our devices, our computer systems, we latched onto the so-called Windows blue screen of death, right? Usually this this memory dump, which you have access to, will have a hexadecimal representation there, right? So these are different use cases, and of course, it's unfortunate that you haven't really started looking at computer networks and the internet, but very, very soon you discover that the representation of so-called IP addresses, right? You know, protocol addresses are represented using specific number systems. For instance, IPv4 uses so-called dotted decimal notation, right? Where each one of these different groupings is, so the 127 is a decimal number, right? 0 is a decimal, 0 is a decimal, 1 is a decimal, right? But with IPv6, things are somewhat changing because the idea behind IPv6, we don't know yet, but the idea behind IPv6 is to enable the representation of slightly more remote devices or network devices. And because the numbers you're working with are significantly larger than with IPv4, the representation is done using hexadecimal, right? FE80, this is hexadecimal. Right? But it turns out that there's actually more things here. And in fact, I'm sure you've seen these on your devices. Sometimes when you access, when you access your phone, your about, you go to your about, is it the settings and then about, you notice that you see strange things like, I don't know if people have bothered to look at things like MAC addresses, for instance, right? If you check this, is it the status or I wonder, it's a status, right? So you go to about, and then you go to your status. In my case, it's on the status. You have access to so-called IP, to so-called MAC addresses, right? Your MAC address is represented using hexadecimal format. And there's more, right? There's more. Very, very soon, perhaps in third year, you discover that certain nifty tools like version control software, such as Git or Mercurial, for instance, will typically represent the commit messages using, I don't know if this is base 36, I think. It should be base 36, but this is a SHA-1 hash, right? It's a cryptographic hash, but these numbers that you're seeing here up on top there, these numbers here, this string here, this is represented using a certain type of number system, right? And if you think about it, you can easily figure out what sort of number system or the different types of characters that are being used here. You notice here that the range of characters that are being used, simple, right? It's A through Z, right? All lowercase, and 0 through 9. If you count these, it's 26 plus 10, which is 36, right? This is what you have here. And I can showcase, I guess, a simple example so that people kind of like get a sense of what we're talking about here. I don't know if you can see my screen.
Yes, we can.
Yes, sir.
Yeah, right. So, I mean, this is what I'm talking about here. If you look at the pattern here, the pattern associated with commit here, all these commit messages here, commit 1, commit 2 here, you notice that there's a pattern here. It's numbers and lowercase alphabetical characters, right? English characters from the English alphabet, all lowercase. And the combination of all these different characters is 26 plus 10, right? Because the numbers you're playing around with here is 0 through 9, if you notice. In here you have 3, 7, 8, 7, 8, 7, 1, 3, 3, 8, 1, 7, 1, 9, 7, 9, 5, 0, 3, 9, 3, right? So all classic examples of how these different bases or numbers tend to be used, right? And it turns out really that this has a very powerful use, by the way. For a particular repository that you work with, each of these commit messages is essentially unique, right? It's a unique representation of the save point you're working with. And so the idea behind version control is that you can roll back to a particular point in time in your repository so that you access content in that repository at a particular point in time in the past, right? Or because of the power of, I guess, commit messages that are represented in this case, is base 36. It gets even better. These links that I've been sharing, I don't know if people have been paying particular attention to this, but usually when I'm sharing links, for the most part, I track those links. I'm interested in tracking how the extent to which people are using or accessing the resource I'm sharing. So I use services that are referred to as URL shorteners, right? There's a whole bunch of them. There used to be a Google URL shortener called Google.gl, right? It's now defunct. It's been phased out. I've since replaced it personally myself with Bitly, right? But there's more out there. There's Tiny URL. So the idea behind this is that if you have a long URL, right, informal resource locator, what you can do is you can shorten it so that people can easily share that resource rather than you sharing something that is going to be multiple characters long like this, right? Instead of me sharing this link here, this link here, which is long, right? Very long. What I do is I shorten it using Bitly, and then what I do is I share this. So this, what you're seeing in line number 10 is the equivalent of this long link here, right? But the key thing here is that the way URL shorteners work is they work in different ways, but the fundamental idea is that there's a mechanism in place that shortens this long URL here into the equivalent shorter version of it. So this. Now, if you pay particular attention to the last bit after the /, you notice that this number system, you notice that these characters are represented using a particular type of number system, for Bitly in this case, right? Now, give it away here, you notice that it's represented using lowercase characters and uppercase characters and numbers as well. Yes?
Is version control the same thing we use when our computer is attacked by ransomware, but we want to restore it at a previous time?
No, that's a different concept. It's different. The idea is pretty much
so
the
that
same,
we can access files before they were affected.
Yeah, no, that's something else. That's different.
No,
Version control
it's not
software
version
is
control. It's
completely
something
different.
else.
You typically use it to. Nope, that's something else. But the idea is the same. What you're interested in is a restore point, right? A particular point in time that you want to go back to. But it's completely different from what we're talking about here. All right. But you've probably seen this as well when you're accessing YouTube, right? So if I go to YouTube, for instance, and I try to access, I don't know what to access here, but guess can access love and monsters. I don't know. Monsters. If we can access a video, right? What you notice is that ideally the original URL, right? It's the same idea, right? I'm just saying here. But this is shortened in easier way. It's the same idea, right? You notice that you have this long URL, but YouTube has an internal service that they use to shorten this URL so that you have the equivalent of that, right? It's much shorter and much easier to work with, I guess, right? And so these are all different applications of number systems. And like I was saying here, for Bitly, for instance, the way that it probably works is because each one of these URLs, so you can get this URL and shorten it, and what you get back, the shortened version of the URL, will be completely different from mine. So the way it probably works is that you use some sort of unique identifier associated with whatever link someone wants to shorten, and then you use that identifier, typically a number, to derive the equivalent base 36 or base 32 in this case, right? It's base 32 because you have uppercase alphabetical letters here. Do you understand this? Application domains, right? Now, in as much as we can go on and on and on to talk about the different usage scenarios associated with number systems, but our interest is going to be on specific types of number systems, specifically base 2, base 16, and base 10, right? So decimal, hexadecimal, and binary, essentially. And so part of why we're doing that is very, very soon, once we start looking at, once we go through a gentle introduction of MIPS assembler, for instance, you'll realize that the simulator that we're going to be using is going to be representing the outcome once we execute code using the simulator in a certain way. So you can choose to represent the output using decimal, using hexadecimal, or using binary, right? Observe, if I open up QtSpim, for instance, we're going to be using QtSpim. What you notice is that it represents, this is what I'm talking about here. By default, if you look at this left panel here, the one I'm highlighting here, immediately notice that by default here, at least my QtSpim, my instance of QtSpim, my integer register representing the values in binary. You see these ones and zeros, but I can change this, right? I can tell QtSpim to say I want these numbers. Pay particular attention to what's happening to these numbers. I want these numbers to be represented using hexadecimal format, right? So I have these numbers being represented as 3000FF10, right? I can also tell it to say I want to represent the values associated with the registers using decimal notation, which is really insane because for the most part, some of the numbers that you're working with are very, very large. And so it's better, it's much more intuitive, at least for the average human being, and most human beings I'd like to think. It's better for you to represent a number in hexadecimal than in binary or in decimal notation, right? Observe. Think about this for a second. Which one do you think is better? Do you want line number 26, 27, or 28? I don't know. I think it's 28 for me anyway, but I don't know what you think yourselves, right? So this is coming very, very soon, right? Where we get to inspect the status of the different registers as we're working with this simulator. But even better, at some stage, once we start looking at specifics of how data is encoded by computers, it turns out that it would be a lot more intuitive for us to better understand what happens under the hood by understanding base 2. Because remember, a computer encodes everything, both data and instructions in so-called ones and zeros. Of course, we're abstracting the idea of flow of electric current here, right? It's saying a 1 could signal the flow of electric current, and the 0 is no flow of electric current, or perhaps a 1 represents a high voltage and a 0 represents a low voltage, right? So for us to be able to figure out exactly how a computer gets to figure out, say this is a red, this is a blue, this is maybe a pink or violet or whatever, we would need to understand base 2, because it turns out that all of these things here, what you're seeing on the right, can be represented using ones and zeros, right? And we see this all the time in these tools that we use, right? I don't know your image editing software of choice, but I use GIMP myself. And when I'm using GIMP, right, and I'm trying to, I'm using GIMP and I'm trying to edit an image, for instance. I wonder if I can find an image. I'm trying to edit an image. Part of what I would do is I'll play around with the colors, right? And when I'm playing around with the colors, right, let's say I want this to be, for some weird reason, I want this to be red, right? This top right, I guess this section here to be somewhat red. What I could do is I could just tell GIMP to say, I don't know if you can see this, but hope you can. I can tell, I'll just raise it slightly here, I guess to 150, I guess. I can tell GIMP to say, listen, GIMP, I want this top right corner here to be represented in a certain color, right? And I'll say fill with color or something. But before I fill with color, I'll change the color code. Now, when I'm changing the color code, observe, I can change the hue, the saturation, the equivalent of red, green, and blue, so that I come up with a particular combination of colors. All of these things, when I'm playing around with these different, I wonder if there's a better way of representing this so that people understand. When I'm altering this different combination of colors, I will arrive at a preferred color, right? Like if I choose red, I know it would be 255 somewhere here or something, right? Here, not exactly right here, but 255 here. If I want to get, I don't know what red and blue give us, but maybe it's, I don't know what that is, but let's say this is what I want, right? This is what I do, right? What I'm doing behind the scenes is I'm just playing around with bits. The numbers you're seeing here, the 255s, if I put 100 here, you can represent these using bits. But it turns out that because a human being would typically be the one working with this sort of software, these numbers are represented in decimal, right? So this is a decimal number here, but this decimal number can pretty much be represented as ones and zeros, depending on the bit depth. Maybe if you're using a bit depth of 8, then the number here, instead of 255, I don't know what the maximum is, but the number here will be represented, the maximum number that you have here will be representative of the bit depth that you're working with. Key takeaway point here is that data and instructions are perceived by a computer as ones and zeros, base 2. A human being can abstract what a computer perceives as ones and zeros into either hexadecimal equivalent representation, decimal equivalent representation, or from a perspective of how the content would be viewed, right? When you more or less like get everything and you combine everything, this is what you have here. But this is just a literal representation of ones and zeros, base 2. It's not just colors, right? Even images can be represented as ones and zeros. In fact, a computer perceives an image as a 1 and 0, right? So, and you've seen this. A typical image like this, like if we zoom in into this image, didn't get any photos of you guys, so we are recycling photos from last year. It's quite sad, really. If you zoom in into a photo, what you notice is as it pixelates, right? You notice that you notice that the image is composed of so-called pixels, right? I don't know if you can see these small little boxes here that you see, small little boxes, yeah? Those pixels can be represented or are represented as ones and zeros, right? Just colors, actually, by the way. So again, application of number systems, right? They're all over the show here. You will soon discover that these things that we type, I'm typing an assignment, right? They said we type it in English or whatever. I don't know if it's Nyanja, if you're doing languages. Those characters that you're working with, right? Those characters that you're working with can be mapped onto the equivalent binary representation, the equivalent of what a computer sees. It's not like a computer sees an A. When you type an A, right? When you type A, or I'm typing ICT, the computer doesn't see I, doesn't see C, doesn't see T. What a computer sees is, when it sees uppercase I, it sees the equivalent of either 73 base 10 or 49 base 16, right? In fact, what a computer sees, when you type I, the computer sees that I as being, let me just change this to numerical representation, 49. What a computer sees is this. And of course, I mean, the representation, the bit representation is dependent on, I guess this would be 8-bit representation, actually. It would be 8-bit. I don't know how to be represented. Yeah, 8 bits. Depends on the architecture, I suppose. But yeah, so this is what a computer sees, right? Stream of ones and zeros. And you can easily tell this, right? If you want, you can prove this by just typing ICT, or let's type I. Save this as I hope this works as a example in coding. Are you still there?
Yes, sir.
Yes, sir.
Okay. If you want, you can. Okay. If you want, you can use hex editors like I use Octeta myself. I've been using it for quite some time for illustration purposes. And if I am to open that file that I just created, which just has an I, you'll notice that, I hope I'll be able to view this. You'll notice that you see that 49 there. I mean, it's the hex representation of I, right? So this is what, and I think I can change the view so that I see, instead of the I see the actual ones and zeros that the computer would probably see or something. I don't know how to, this is the thing, this is the problem when you use this tool. Oh, there we go. When you use this tool once a year or something, right? So this is what I'm talking about here. Instead of the I just opened this file that I just created. You notice that the representation is 0, 1, 0, 0, 1, 0, 0, 1, right? And you see that 0, 1, 0, 0, 0, 1 is the equivalent of, if I come here, 0, 1, 0, 0, 1, 0, 0, 1 is the equivalent of 49, right? It's just that there's a leading zero here because it has to be 8-bit representation usually. Is this making sense? I wonder what 1000 is here. Look at this, right? The last part that's there, it's probably like some carriage return character or something. So the 00001010 is like 1010. 1010 is like A, right? So you go to your, you can just go to your ASCII table and check what A is, and A hexadecimal is in A, right? Decimal number 10. You check for decimal number 10 and you see that it's a line feed, right? So it's like that. When you create, typically when you create a file like this, depending on what sort of tool you're using, there'll be a line feed character, a marker that the operating system uses to identify the end of the line or something. So it's a line feed, which is why my file here, Octeta thinks that my file has actually 2 characters, but the last one is a carriage. It's a line feed, right? This thing here at the end. Is this making sense? So just showcasing different areas, I mean, different applications for these things, right? If you want to find out more about the ASCII table, if you want to go ahead of the rest of us, you can look up the ASCII table and just, I wonder if ASCII, I didn't know there was ASCIIcode.com and ASCIItable.com. You can get ahead of the rest of us, even though we do discuss the data encoding when we look at how text is encoded. And so we talk about things like the ASCII table. We discuss the ASCII table, for instance, and different other textual encodings like UTF, so that we get an understanding of how this is done. So if you're curious, I do encourage you to think this is this the Wikipedia page, or maybe you should go to, this is good. ASCIItable.com is good. I do encourage you to go to ASCIItable.com. Okay. Key takeaway point here is application of number systems, right? And this is coming back to Roost. All right, so now that we've set the stage for different types of scenarios, at least insofar as computing is concerned, where we use number systems, I guess now would be a time to do some revision, bases, right? I know we did base 10, base 16, and base 2 in grade, I don't know if it's grade 3 now, but I know we did this. So it's going to be a bit of revision, just to remind us of what we did. And here's the thing, right? When you were doing this, I'm sure you were asking the teacher, or maybe you were discussing amongst yourselves, why are we learning this? Well, you now know, right? So that you could reuse that knowledge in ICT 1110. Great. So unless if there are any specific questions, no? All clear. So we'll start with the easiest one, which is base 10, right? Now I'm just regurgitating what Miss Banda taught you in grade 3, right? When she told you that the idea behind decimal notation or base 10 is that you are essentially, it's called base 10 because you're working with 10 symbols. They're not digits, they're not numbers, they're just symbols, right? Those symbols could just as well have been sticks. And in fact, there are certain human civilizations that will count like that, right? So the symbols will range from 0 all the way up to 9. Everything else that comes after is a derivation of these 10 symbols, right? So 10, for instance, is a combination of the symbol we call 0 and 1, right? 123 is a combination of symbols 1, 2, and 3, right? Another interesting thing about so-called base 10 or decimal notation is that as you are making use of more than one symbol, it turns out that placeholder associated with the symbol has a certain significance associated with it, right? So because we're working with base 10, you have from right to left, you would have a ones place, a tens place, a hundreds place, a thousands place, right? And you go on and on and on. You're just multiplying by 10 essentially. Right. So the idea, it turns out, is the same when you're dealing with hexadecimal and binary notation, right? This is part of the reason why we're saying this. They're just symbols, right? We're just playing around with symbols. Why do we use base 10 when we can use base 2, right? I don't know. I'm guessing it would require a radical change in mindset to tell people, to sell this idea to people, to say we must start counting using base 2, not base 10, right? So ask you, how much did you buy your data bundle at, right? Well, it's not 200 kwacha, it's actually 11001000 or something. Anyway, right, and what I was talking about at the bottom here is how you get to, I guess, arrive at a number like 1110 or something. All right, so base 16 works in more or less the same way. So it's base 16, otherwise called hexadecimal. Base 16 because you're working with 16 symbols. And the symbols that you work with are the symbols 0 to 9, and then A to F. Right, so if you count those, 0 to 9 is 10, and then A to F will give you 6. So in total, you have 16 symbols that you work with. And so beyond F, you essentially recycle these 16 symbols. And I'm sorry I'm using the word digit here. This is supposed to be symbol. It must sink in, right? It's supposed to be symbol. Although you can use digit here, but it's supposed to be symbol, essentially. It's a symbol. Right. The interesting thing about base 16 is that each symbol from A to F can pretty much be represented by decimal number 10 through 15, right? That's one interesting thing about it. And it turns out that's a useful concept when you're trying to convert from either hexadecimal to decimal or hexadecimal to binary, right? The other interesting thing, especially when you're dealing with conversion from hexadecimal to binary, is that each hex symbol represents what's called a nibble, right? Or 4 bits, essentially, right? So this A here can be represented using 4 bits, ideally. Very powerful concept, because it turns out that conversion from a number such as 3E8 is much, much easier, because you can easily represent these symbols, these individual symbols here, with nibbles, right? Equivalent nibbles. Ideally, groupings of 4 bits. Do you understand this?
Oh, not yet, Dr. Lighton. On that part, when you say each hex digit represents 4 bits, are you talking about the hex digit on the 6th place that will represent 4 bits, or what do you mean by that?
No, I mean, like, if you have a number, a hexadecimal number, such as if you have a, can we have a hexadecimal number H? Kapala, can we have a hexadecimal number H?
No.
Okay, right. All right. So what we mean, yes, the Kapala is right. What we mean is, if we have a number, a hexadecimal number like F9, for instance, we can represent F9 with groupings of each one of these symbols here, right? This can be represented using 4 bits. This can be represented using 4 bits as well, right? 1, 2, 3, 4. 1, 2, 3, 4. Of course, I mean, I'm not saying that this is actually going to be 4. We need 1's place, 2's place, 1, 2, 4, 2, 0, 1. So it'll be like this, right? Yeah. This is 0, 1, 2. Yeah. This is 9, is it? Don't worry, we'll convert this. It doesn't matter if it's correct or not anyway. And then 15 can be, 15 is equal to, 15 is obviously going to be equal to 8 plus 4, right? Plus 3 or something. This is actually 16, I think. This is actually 15 to 16. You understand what I mean? So what we mean is that, I think so, it should be. What we mean is, it doesn't matter if it's correct or not, but what we mean is that, each one of these symbols, when you have a hexadecimal number like F9, F can be represented using 4 bits. 9 can be represented using 4 bits, right? 4 bits, 4 bits are referred to as a nibble, right? 9 can be represented by 4 bits as well. It's very powerful. I made a mistake here, the one at the end, right? Very powerful concept, because conversion, direct conversion from hexadecimal to binary becomes a lot easier this way. So this is what we mean here. All right. So conversion from hexadecimal to decimal is pretty much easy, right? Even more easier when you're working with symbols from, when you're working with the basic building blocks, the 16 symbols, so 0 through 9 and A through F. Why is it easy? Because all you do is you just get the equivalent decimal representation associated, or the mapping associated with those hexadecimal symbols. So a 0 is a 0, a 1 is a 1, a 2 is a 2, a 3 is a 3, 4 is a 4, a 9 is a 9. But an A is a 10, a B is a 11, a C is a 12, a D is a 13, an E is a 14, and then the F is a 15, right? And so using these symbols, you can easily come up with a direct conversion here, right? Which is pretty much intuitive. But this only applies when you're working with a single symbol, right? So if we say, what is the equivalent of a B? You know that you just have to form a mental picture of what sort of decimal number represents a B, and you see that this is an 11, then you know that the answer is going to be 11. single digits, right? An E is a 14, an F is a 15. Whatever. But once you start working with derivations of hexadecimal symbols beyond one symbol, you have to do things slightly different. And it turns out that there's a formula that you have to follow, right? Easiest method is to take advantage of what's called repeated multiplication, right? And we go through examples here so that we understand. The idea behind repeated multiplication is you just repeatedly multiply the radix with the hexadecimal numbers, and then you add them up to get the total equivalent of your decimal number, right? So this is a formula, right? You first of all, given a hexadecimal number, you first of all convert all the hexadecimal symbols to their equivalent decimal symbols. This is in the case where you have some symbols, such as symbols from A to F. If you have a hexadecimal number like 56, for instance, right? 56 in hex. There's no need for you to convert the symbols to the equivalent decimal because they're already converted to decimal, right? 5 is 5, 6 is 6, right? But if you have a number such as F9, for you to be able to convert F9 to decimal, the first step is you first of all convert the symbols, a symbol like F to its equivalent decimal. This would be 15, 9, right? And then you go to step number 2. Step number 2 is you start multiplying the numbers that you converted here by their mapped on powers of 16, right? Beginning with 16 to the power 0, essentially. And so you do this right to left, right? So you arrange your number just like you would a decimal number, left to right, and then you associate the powers beginning 0 from right to left. This will make sense once you go through an example if you've forgotten your basic number system, mathematics or arithmetic that you did in primary school. And then the third step, the final step, is you just add up the result of you multiplying the numbers with their powers. So observe, this is what we mean here. If you have a number like A2DE, this is a hexadecimal number, right, base 16, and you want to convert it to base 10. First thing you have to do is you convert the symbols, the hexadecimal symbols, into their equivalent decimal symbols, right? A is what? A is 10,
10.
B is 11, C is 12, yes. D is 13, E is 14, F is 15. So first step is you convert these hexadecimal symbols to the equivalent decimal symbols. A is 10, 2 is going to be 2, D is 13, E is 14. The second step is you're going to multiply these converted numbers here by their respective powers of 16, beginning with 16 to the power 0, right? So we are going to say 14 times 16 to the power 0, 13 times 16 to the power 1, 2 times 16 to the power 2, 10 times 16 to the power 3. You get the results, and then you multiply, and the visualizations here are a bit messed up here. You get the result after, so you multiply this and that, you get, you get the result of this 16 to the power 0 is 1, 16 to the power 1 is 16, 16 to the power 2 is 256, 16 to the power 3 is 4096, and then you multiply these numbers here, right? After you multiply these numbers, you add them up to get the result.
Sir,
Yes.
may you kindly go through the calculation and the conversion, please?
Which calculation?
The whole table. After you convert them to their respective powers, their hexadecimal equivalents,
Yeah, okay. Right, so what we're saying is you get the equivalent, the decimal equivalent of these hexadecimal symbols. A is 10, 2 is 2, D is 13, E is 14, right? The next step is you're supposed to multiply the powers of 16 associated with these placeholders here with these numbers, right? So in fact, we jumped a step. What you're supposed to do is you compute the powers of, the next step is you're supposed, if you do this stepwise, you identify the powers of 16 that you're working with. Afterwards, you evaluate the powers of 16, right? Once you evaluate the powers of 16, you multiply the result of the evaluation of the powers of 16 by the equivalent base 10 numbers that you derived here. So it would be 10 times 4096, 2 times 256, 13 times 16, 14 times 1. We have another example. Maybe it will make sense if we go through another example. And then as a final step, you just add the result of you multiplying the decimal equivalents with their powers of 16 here, right? So you add these up, and then the number that you get here is your equivalent base 10 number. It's not that hard, just repeated multiplication, right? So what we're saying is A2DE base 16 is equal to 41,694, right, base 10. So here's another example. Let's say we want to convert 3E8. Same process. The first step is we need to get the equivalent base 10 symbols for each one of these symbols associated with the number we are converting. 3 is going to be 3, E is 14, 8 is 8, right? Again, I just want to mention here that there's no easy way of remembering what an A is, what a B is. You just have to commit it to memory or something. But it's easy because you know that if hexadecimal works with the same first 10 symbols as in decimal, so it's 0 to 9, and because you're working with base 16, for you to get 16 symbols, you need 6 additional symbols. If those symbols are represented using the alphabet, you just need to count 1, 2, 3, 4, 5, 6, right? Easy way of remembering here. Anyway.
So,
Yes, sir.
is there a way you can move from hexadecimal to binary without having to do with base 10?
Yes, and we discussed that. We're jumping the gun, but there is a way. Because if we're saying that you're representing, if you're representing in an implicit way, if you can represent a hexadecimal symbol using 4 nibbles, I mean four binary placeholders, which is a nibble, then you can easily convert. You can easily convert it to binary. Although implicitly, what you do actually when you're converting it to binary is it's like you're going to you go from hexadecimal to decimal and then to binary. But it turns out that when you're converting the 16 symbols to decimal, or you're converting the equivalent decimal values of the 16 hexadecimal symbols, it's much easier to convert those 16 symbols into binary. You can actually easily form a mental picture of that, right? So, but we'll talk about exactly how you get to how you convert from hex to binary. Surprise, surprise. The easiest way of converting from hex to binary is using a calculator, right? Yeah, you can write a program or something. I don't know. That was a joke. So anyway, so here's another example, right? So we're saying 3E8. The first step is you first of all identify the equivalent decimal symbols associated with these hex symbols you're working with. So 3 is 3, E is 14, 8 is 8. And then you identify the placeholders here, right? the powers of 16 you're working with. 16 to power 0, 16 to power 1, 16 to power 2. You evaluate the powers of 16, right? So essentially, you're getting the result of what is 16 to power 0, it's 1. 16 to power 1 is 16. 16 to power 2 is, I don't know, let's use the calculator, right? This is what we're doing. No, not 16 times 2, 16 times 16, 256. Okay. So do this stepwise. It makes more sense if you do it stepwise. So you get the symbols, and then you get the powers of 16, evaluate the powers of 16, and then multiply the derived decimal equivalents of the hex symbols with the evaluated powers of 16. 3 times 256, 14 times 16, 8 times 1. And then you add these up. 768 plus 224 plus 8, right? And then you get 1,000. So what we're saying is 3E8 base 16 is equal to 1,000 base 10. You understand this? I mean, it's not that hard. I mean, so a tricky thing is people normally get confused when you have the situation where somebody tells you convert 823 base 16 to 823 base 16 to binary, right? Some people get confused with this. They'll think it's still 823, right? Because it turns out that there are certain symbols, certain hex symbols that are shared with the decimal notation, right? You have to do this stepwise. Step 1, get the equivalent symbols, right? So if we have 823 hexadecimal, 823, what we do is we get the equivalent decimal symbols, which are still going to be 8, 2, and 3. Okay? Get equivalent decimals, right? So you get the equivalent decimals, what do? You identify powers of 16, right? From right to left, 16 power 0. 16 power 1. And 16 power 2, right? So you get the result of 16 to power 0, 16 to power 1, we know that 16 power 0 is 1, 16 to power 1 is 16, 16 to power 2 is 256, right? Evaluate powers of 16. 1, step 2. This is like we are it's retarded. I don't know why we're doing this. Many people are already bored here. Okay. And then what you do next is you multiply decimal equivalent symbols with powers of 16. In this step, all we are doing is we're saying 256 times 8, 16 times 2, 1 times 3. And then step 5 rather, add or product. You get the sum of products, right? And essentially you just say this plus this plus this. Then you get that. So here's the thing, 823 base 16 is equal to 2083 base 10, right? And of course, I mean, if you have a calculator, I guess you could, then if we have 823, and then you convert it to equivalent decimal number or something, right? The key thing is just to really just ensure that you follow through with the steps, you master the step, and then you should be fine. Yes, sir.
is it ever the other way around where you have to convert from base 10 to hexadecimal?
Yeah. Yes. In fact,
Do
it
you have
turns
an
out
example for that?
yeah, it turns out this is what we're supposed to start covering. We are going to do this at the time here. I'll let you guys play around with some examples. There are quiz questions from last year, before last year. There are questions from the exam. I would like to encourage you to go into the Moodle, play around with those numbers, try and see if you can figure out, just if you play around with at least 3 or 4, maybe 5 conversions, you should be fine. And then tomorrow, I think we have class at, is it 18 or something? Yes, tomorrow.
The calendar doesn't change, sir.
Yeah, I don't know which calendar you're looking at, but last time I checked, the calendar I was using had changed. So tomorrow we will continue. Mike, the calendar has changed. We have class at 17. I don't know which calendar you're using. The calendar is here. It's here. So tomorrow we will continue with what somebody was asking, as in how do we convert from decimal to hexadecimal. It turns out it's easy. It's just repeated division, right? We'll look at this, and then hopefully tomorrow we can also quickly transition and start looking at binary representation, base 2. Unless if any questions, I'm going to end here and just let you to just try and see if you can get up to speed with what we looked at, because it turns out that some of the things we are going to cover tomorrow, on Sunday, and on Monday are going to be somewhat related to this. Because what we're doing between now and Monday, I guess, for the most part, is just doing this conversion. So hex to decimal, decimal to hex, hex to binary, binary to hex, binary to decimal, decimal to binary, you know. So you want to make sure that you understand this. Unless if there are any questions?
Hello, sir.
Yes.
On your slide 34,
Yes.
there is a box where you represented letters in small letters and others in capital letter. So is there a difference or it's the same?
Great question, Ms. Namwila. So it turns out that the representation of these numbers is not case sensitive. Usually, though, by convention, most applications, most literature that you find online will present these hex symbols A through F in all uppercase letters. But in this example, I know this example is from QT-SPIM. What QT-SPIM does is it represents everything in lowercase letters. So observe. If I say change this to hex, right? This is what you're seeing here. This is why. So there's no difference. Thank you for asking that nice question. Thank you very much. Brilliant question. These are questions you should be asking, right? There's no difference. I wonder if this is coming from the, oh no, Unix is case sensitive, right? Thanks for that question, though. Are there any other questions?
Just to clarify what Namola just said. So whether uppercase, lowercase, just hold the same value.
Yes, it's the same value. This is, the symbol is still going to be A. We're just saying the A symbol represents 10, B represents 11, C represents 12, D represents 13. And you see this in most applications, actually, right? Like when I was talking about IP addresses, right? If you look at this this IPv6 representation here, observe this is being represented in all lowercase letters, right? All lowercase letters. FE80, 3F8C is the same thing. It is the same thing. Anyway. All right. Any other questions? Okay. See you when you see me. I think I did mention, I don't know if I mentioned just day before yesterday that there's a quiz on Tuesday. I hope you're preparing. So I'll see you tomorrow then at 17 hours promptly. Bye-bye. Thank you.
Bye, sir. Okay. See you guys on Monday. I'm out.